Hello everyone and welcome to another Advanced Star Maths differentiation video. In this video we're going to take a wee look at understanding what an inverse trig function is and how to differentiate them. Now the success criteria for this, let's have a wee look. What we're going to do is we're going to make sure that we know the standard derivatives for inverse sine, inverse cos and inverse tan. In particular, we need to know that most of the time when we're differentiating using inverse sine, inverse cos and inverse tan, we need to use the chain rule. And within that you might find, and I've got some of the later examples in this video are involving using the quotient rule and product rule as well. And then the bit everybody finds quite tricky, simplifying the answer fully. So let's have a look. Let's have a wee recap though from higher, okay? Let's have a wee think about inverse functions for a second. Basically the graph of an inverse function, remember, to draw that you reflect the graph in the line y equals x. And the quick way to do that would be to take all the x and y coordinates and swap them around, essentially swapping the x-axis for the y-axis. And the graphs of the inverse trig functions can be shown in the same way. So here's a graph of inverse sine x, or arc sine x, as it might sometimes be referred to. And what we've got here is, remember, you should know the graph of sine x very, very well. It would have a domain usually from 0 to 2 pi, and the range is -1 to 1, because that's the maximum and minimum values. But since we've swapped the x and y axis around, what I'm showing you here is the domain. The domain goes -1 to 1. So remember they're the x values, the input values. So although that used to be the range for sine x, for the inverse function, the range becomes a domain, and vice versa. So the input values range from -1 to 1, and the range, well, I've just selected a range here of -pi/2 to pi/2, so -90 to 90. And if you were to kind of rotate your head slightly 90 degrees, you would actually see that from 0 to pi/2, that is almost kind of the same graph anyway. So you kind of build up a picture there. As we look at inverse cos, so the inverse cos graph looks like this. This time I've selected a range of 0 to pi, and a domain of -1 to 1, and inverse tan x looks something like that. You will very rarely, you won't need to reproduce these graphs, not in the same way that Nat 5 and higher, you're asked to sketch trig functions and things like that. That's not really something you're asked to do too much of. You are asked to sketch functions, right enough, but they're very rarely trig functions. So, but just give you a wee visual picture of what you're dealing with. What we need to really take an in-depth look at this lesson though is differentiating inverse trig functions. So let's take a wee look at how to differentiate inverse sine x. Well, the proof for that, so it starts off like this. Let's let y equal inverse sine x. Okay, so by definition, if y is equal to the inverse sine of x, then x must be equal to the sine of y. Okay, now that lets us find, if we were to differentiate that line, that would let us get dx by dy. That would just be cos y. Okay, okay, that's fair enough, but we want dy by dx. Well, dy by dx will be the reciprocal, so dy by dx is 1 over cos y. Okay, but we want the derivative in terms of x. That's what we would prefer. So what we need to do is do a little bit of messing around and see if we can get an expression for cos y in terms of x. And to do that, what we're going to do is take that line of work in there and produce a right angled triangle for it. Okay, so the angle is y, the sine of y, right? The angle is y, and that really, if you think about that, that's sine y equal to x over 1. Right, so that's the opposite over the hypotenuse, that's x, and that's 1. Okay, that would let you get an expression for the cos of y being adjacent over hypotenuse. Right, well, what's the adjacent side? Well, work it out using the same way you would work out any missing side to a right angled triangle. Let's use Pythagoras, and you'll work out that that is square root hypotenuse squared, take out the opposite squared, so 1 squared, take away x squared, which is root 1 minus x squared. Okay, so cos y is adjacent over hypotenuse, so root 1 minus x squared over 1, so cos y is root 1 minus x squared. Right, so let's use that over here, and what we get is the derivative in terms of x is 1 over root 1 take away x squared. Job done. Okay, and that is your standard derivative for y equal to inverse sine of x. Now, a very similar proof can be used for the other two inverse trig functions, inverse cos of x, inverse tan of x, and you see them here. They are on the formula sheet, folks. They don't need to be memorised, but you know, well, a lot of people do end up memorising them anyway. It's quite easy to remember. So inverse sine of x is 1 over root 1 minus x squared. Inverse cos of x is negative 1 over root 1 minus x squared. You need to be very, very, very careful when you're doing questions involving inverse cos of x, because one negative sign dropped and you start working with the derivative for inverse sine of x rather than inverse cos of x. So be very, very careful. And inverse tan of x, usual, looks completely different to all the other ones. 1 over 1 plus x squared. It's actually easier to work with. So that is the three inverse trig functions, the three derivatives of the inverse trig functions that you need to learn. So let's start playing around with some examples for this thing. So what have we got? We've got y equal to inverse sine 3 of x. So the fact that it's inverse sine 3 of x means we're going to have to use a chain rule, as a function within a function, to differentiate it. So we don't need all the kind of long-winded working for the chain rule though, because we know the derivative of 3x is just 3, so we're going to multiply by 3. So dy by dx, nice and easy, is the derivative of the inverse sine 3x part, 1 over, so the standard derivative, remember, for inverse sine of x is 1 over root 1 minus x squared, so root 1 minus, now this is where you need to be very careful. This is your x part, this is your angle, if you like. That needs to go in place of x, like that. Okay, you have to be very, very careful when you're doing that. Okay, so what's that going to come to? Right, I've just stuck a thinner pen on there because there's going to be a lot of writing comes up for some of the next few examples. So, oh, I forgot to times by 3. Hang on, get rid of that. So times by the derivative of 3x times by 3. So we end up with 3 over root 1 minus 9x squared. Job done. Okay, so two important things there. Use of the chain rule needs to be remembered, and this part has to go in place of x and then has to be squared. Okay, so look at the next one. Inverse cos of x squared. Right, that's the way we look. So the standard derivative for inverse cos of x is the same as the inverse sine of x, but it's negative. So we'll say dy by dx equals negative 1 over root 1 minus x squared squared times the derivative of x squared, so times 2x. So tidying this up, there's two parts we need to look at, tidying up the squaring and then just combining the multiplication, so we get negative 2x over root 1 take away x to the power of 4. Happy days. Next one. So let's start making things a wee bit more trickier now. So this is inverse tan root x. So we have to deal with, straight away I would normally just write that as inverse tan x to the power of a half. Okay, so you're going to have to differentiate it anyway as part of your chain rule. That has to be differentiated. So dy by dx. So the derivative for inverse tan is a wee bit easier. 1 over 1 plus. Now, I know I've written it as x to the power of a half here, but if you look at this, right? This is root x, and root x is going to go here squared. So that's actually quite handy because we know that that's just going to become x on the next line, so that's not too bad. Times. Now, we need the derivative of x to the power of a half, so that is a half x to the power of negative a half. So we've got quite a bit to tidy up here. Tidy up the first part, 1 over 1 plus x, that's easy enough, times 1 over 2 root x. Okay, positive powers always are better. Positive powers and root signs, really. So, finishing it off, just combine the denominators there, that's going to be 1 over all of 2 root x, bracket 1 plus x. Job done. Okay, so those three there, they're pretty box standard. Sort of minimum competence shouldn't be giving you too much of a hassle. Now, ones like these next couple of examples require a lot more care when you come to simplifying them. Okay, so let's have a look at this. Now, the fact that that's negative 1 over x makes that quite a tricky thing to deal with. All right. But what we need to do is probably just write this as inverse sine minus x to the power minus 1. Oops. Okay. And just treat it like that. So the derivative dy by dx, well, the derivative is 1 over root 1 minus x to the power minus 1 squared. Okay. Times by the derivative of minus x to the minus 1 squared. So if you think about it, probably just do this bit in your head, right? And you would just say, well, the derivative of that would be positive x to the power minus 2, right? So x to the power minus 2. Right, so we know that's going to become 1 over x squared on the next line. But also, we need to deal with this as well. So what we'll have is 1 over root. Now, we're squaring something that's negative here, so that's going to become positive. So the effect on the subtraction here is going to leave that as it is. So it's still going to be 1 take away, but it's going to be x to the power negative 2 this time. Okay, times 1 over x squared. Now, the tricky thing about this is what we would prefer to have is terms under the root sign with positive powers. So the way to deal with that is, again, if I just do a wee side bit of working over here, if we treat 1 minus x to the power minus 2 as 1 minus 1 over x squared. Okay, and then combine these into a single algebraic fraction. So that's going to be x squared over x squared take away 1 over x squared. So x squared take away 1 over x squared, right? And that is going to be substituted in place of that expression. So the next line of the derivative is going to look like this, 1 over root x squared take away 1 over x squared times 1 over x squared. Right? It's quite a common technique to not bother combining anything until you've got both parts really simply written as possible, because it just makes your life a bit easier if you get both parts simplified first. So there's some further simplifications we can make to this. We can use our surds law and split the fraction on the denominator there into root x squared take away 1 over root x squared. And the benefit of that, of course, is that we get to write, we get to then take the square root of the x squared. So we'll have 1 over root x squared take away 1 over root x squared times 1 over x squared. So we can take the square root of that. So we now got 1 over. Takes a while, this takes quite a wee while, but you just have to be careful not to make mistakes as you go. Root x squared take away 1 over x times 1 over x squared. And then almost there, 2 more steps to go. Now, if we're dealing with this, that x is going to go into the numerator, right? And we'll finish off with x over square root x squared take away 1 times 1 over x squared. Right, now we can tidy this up. One of those x's cancels with one of those x's, and we're going to end up with 1 over x square root x squared take away 1. Okay, quite a job getting that simplified from there, but you see the sort of the general gist of things there. We can combine what's under the root sign here into a single algebraic fraction, and then use our surds rules to help us tidy that up. Right, well, let's have a wee look at another one, log 1 plus inverse cos x. Now, this one's quite quick to do because you should remember the standard result for the derivative of log of f of x. Yeah, the derivative is f dashed of x over f of x. That's the standard result for the derivative of a log. So how does that look to this? Well, dy by dx is equal to the derivative of 1 plus inverse cos x. Well, that's easy enough to get because the derivative of 1 is nothing, and the derivative of inverse cos x is negative 1 over root 1 minus x squared. Okay, and that's all over f of x, so all over log 1 plus inverse cos x. Right, so the way to tidy that up next is just to write it actually almost kind of as is, not too much to do here. This is the final answer, negative 1 over root 1 minus x squared log 1 plus inverse cos x. And that's it. That's all you have to do. Right? So it's quite easy, that one. Okay. Right. So got one more for you. Now, what I wanted to do was I didn't want the video to drag on for too long, right? So what I've done is in the notes there is an example for y equals x squared inverse cos root x, and I thought I'll not bother going through that in the video because it's quite self-explanatory when you look at the notes. Essentially, it's a product rule question, um, and the derivative of u and v are quite easy to get, and in particular the hardest part of simplification is actually quite straightforward with that one. So what I thought I would do to cut the length of the video down, I would do the last example in the notes, and spend a bit more time on that one. Okay, because it is pretty difficult. If you get this, then this is definitely a grade AB question in the exam for sure. Okay, so let's have a look. If you were to start differentiating this, right, you might start off with, right, dy by dx equals, well, it's inverse tan, so that's going to be 1 over 1 plus all of this squared. So we're going to have 1 plus sine x over 1 plus cos x squared times, blast it, times the derivative of this. You've got to be kidding. So this is a classic example of one where really you need to be, we haven't done it yet for any of these, but you have to really help yourself by using the notation for the chain rule and planning this out. Okay, so let's start with letting u equal 1 plus sine x over 1 plus cos x. And the beauty of that is that that means that y will equal inverse tan u, and so dy by du will equal 1 over 1 plus u squared. Right, that's the easy part. Let's park that for now. We need to now differentiate this. So I'm not going to use u and v again because I don't want to get confused. We're going to say let a equal 1 plus sine x. So a dashed is cos x. Because of course the only way to differentiate 1 plus sine x over 1 plus cos x would be to use the quotient rule. Okay, so b equals 1 plus cos x, b dashed equals minus sine x, and b squared equals 1 plus cos x squared. Right, let's do this. Quotient rule. So this is going to be du dx. Right, important to get that notation correct. Keep yourself right, if anything else. So du by dx will be that times that. 1 plus cos x times cos x. So that's cos x times 1 plus cos x. Okay, so far so good. Take away that times that. But I'm taking away negative sine x times that, so that's going to become an add. Sine x 1 plus sine x all over b squared 1 plus cos x squared. Alright, so let's do some work to tidy this up then. Because we're obviously going to get cos squareds and sine squareds and things, and hopefully they're going to end up cancelling out. So multiplying out the brackets, that's given us cos x plus cos squared x plus sin x plus sine squared x all over 1 plus cos of x squared. Right, nearly there. The cos squared and sine squared, that's going to become 1. I'm going to end up with cos x plus sin x plus 1 all over 1 plus cos of x squared. Right, so that's du by dx, and we've got dy by du, that's up here. So the derivative, right, brace yourselves for this one, the derivative, oh, what's going on with my screen? Right, so dy by dx is going to be du by dx times dy by du. Right, 1 over 1 plus u squared times cos x plus sin x plus 1 all over 1 plus cos x squared. Whew. Right. I wish I could say we were near the end, because we still have to plug 1 plus sin x over 1 plus cos x in place for u there, and then get all of that simplified. Right, so we're going to have to keep going with this. Not sure why this line keeps reappearing, it's a bit annoying. Let's continue on then. Right, let's get u replaced. So we're going to get 1 over 1 plus, what will it be? 1 plus sin x, yeah, 1 plus sin of x over 1 plus cos of x all squared times cos x plus sin x plus 1 all over 1 plus cos of x squared. Right. Now, how do we tidy this up? Well, the easiest thing to do, let's work with the product on the left hand side. Let's have 1 over 1 plus, right, now I'm going to treat this as 1 plus sine of x squared over 1 plus cos of x squared times cos x plus sine x, get fed up writing this, plus 1 over 1 plus cos of x squared. Right. The reason why I've done that is because I'm similar to something I did in one of the earlier examples. What I'm going to do is combine the denominator there into one term. So what am I going to get then? I'm going to get 1 over, now this value of 1 here is going to be 1 plus cos of x all squared over 1 plus cos of x all squared. So what I'm actually going to get is 1 plus cos of x all squared plus 1 plus sine of x all squared all over 1 plus cos of x all squared times cos x plus sine x plus 1 all over 1 plus cos of x squared. Whew. Right, hopefully having written that line out, you're going to see where this is kind of heading, because that term is going to go up onto the numerator, and we're going to get 1 plus cos of x squared on the numerator there. That's going to cancel with the 1 on the other side of the times sign. So 1 plus cos of x squared plus 1 plus sine of x squared times, I'll write this out again, times cos x plus sine x plus 1 all over 1 plus cos of x squared. Now, to be fair, I'm probably going around this in a slightly long-winded way, you know, in terms of the amount I'm writing in each line. I probably could have gotten away with a little side separate bit of working to simplify this, and then sort of take it for there and come back to it. But you know, I've chosen that would have saved me writing this out all the time, you know. But it's fine really the way it is. So let's, almost there at the end, right? Let's get to the finish line. Okay, so this simplifies down because obviously that and that are going to cancel. And what I'm going to end up with is cos x plus sine x plus 1 all over 1 plus cos x squared plus 1 plus sine x squared. Now, still not entirely happy with that because really those square brackets on the denominator could really be doing we get multiplied out and tidied up. So cos x plus sin x plus 1 all over, right, let's square these out. So 1 plus 2 cos x plus cos squared x plus 1 plus 2 sin x plus sine of squared x. Right, the cos squared and the sine squared are going to become 1. And let's tidy up what we get from there. So we're going to get the numerator cos of x plus sine of x plus 1 over 1 and 1 makes 2 plus 2 cos x plus 2 sin x plus 1 for the sine squared plus cos squared. So a final line of working just to finish tidying it all up. Cos of x plus sine of x plus 1 over 2 cos x plus 2 sin x plus 3. Phew. Right? Takes ages to simplify something like that, and again, there will be a couple of them in that exercise. It might go down this line with you. You just need to be patient. You just need to take it kind of on the chin, all right, and be patient with it. And if you need a hand, drop me an email, and I'm more than happy to share the solution with you. Okay, so well done, and I'll see you in the next video.